Topic 8.2, now that we know how to identify acids and bases, we're going to look at, well, what are the properties of acids and bases and how can we use those properties to determine a reaction and what the products of those reactions look like, so on and so forth. All right, remember, acids are represented as a hydrogen ion in an aqueous solution because they have dissociated into that. Bases, they neutralize acids. And one product of all base or neutralization reactions is the production of water, the majority of the time. Different kinds of bases that we're going to specifically look at and the reactions in which they run are metal oxides and hydroxides. So that can include like MgO, because that is an oxide, versus MgOH2, that is a hydroxide. But both produce the same products. Ammonia, soluble carbonates, and so because carbonate's insoluble usually unless it's with an alkali metal, so that includes Na2CO3 or K2CO3, those are soluble. And lastly, hydrogen carbonates, and so that is when you have, again, NaHCO3 or KHCO3, because that hydrogen makes it a hydrogen carbonate. Go figure. Now, there are more specific branches of bases called soluble bases, and these are alkalis. That's what they're also known as, because when these bases are dissolved in water, they release that traditional hydroxide ion that we associate a base with. All right, so an example is if you have K2O, right, and we put that into water. That is going to cause, because we're making an aqueous solution, we're dissolving it, it's going to cause K plus OH minus. Okay, and so here, due to putting this solid metal oxide into water, it causes a small reaction to take place, and we get a cation, and we get that hydroxide. And it's this hydroxide ion that we really have to watch out for because that is what kind of signifies a strong base, and we need to be wary of it. Okay. Another example is if we have NH3, and it's already in its aqueous form because ammonia is a liquid. Well, it's not a liquid, it's aqueous, and we have water, and that produces NH4 plus and OH minus. So once again, here's that hydroxide. Now, not all bases and not all neutralization reactions will actually produce a hydroxide. All right, so that's something you just need to keep in mind. So you have like bases, and one segment of that base are going to be your alkalis that produce an OH ion. And so, again, not every base has to produce that, but that is characteristic of a strong acid-base reaction. So looking at how acid-base reactions operate. So if you have your parent base, so that's the base you're originally putting into your reaction, and you have your parent acid. All right, giving you an example, let's use NaOH. So we have our strong acid, strong base. Now, if you take a look, okay, that OH and the H from the acid and base, that makes H2O. And that Na and Cl from the base and the acid makes NaCl. It makes a salt. And so that is very characteristic of an acid-base reaction, is you typically make water and you're going to make a salt. And that's kind of how it works. So one type of reaction, you have an acid plus a metal, and this is a pure metal, not a oxide, not a hydroxide, just pure metal. So when you put an acid or put a metal into an acid, as you guys know, it's going to bubble. We've done this with magnesium, ribbon, and hydrochloric acid, right? And so when you get a reaction, you have, let's just say 2 HCl We're going to add some zinc. And we're going to get a salt, zinc chloride, and it's going to bubble, and it's releasing hydrogen gas. All right? So what I'm going to go through and show you is what's called a net ionic equation. So we know what's important in a reaction, what's actually partaking, and where ions are going. In topic 9, we talk a lot about ion movement, and acids and bases, and those reactions have a lot of ion movement, which is why we can use electrical conductivity to help us determine what's a strong acid, weak acid, so on and so forth. And so there's this concept called a net ionic equation. So we take anything that is aqueous and we separate it out into its ions. So that means we have 2 H plus and 2 Cl minuses. Zinc is a solid, so it's not in an aqueous solution, so it stays. Do the same thing with the products. So zinc is aqueous, so it's in its ion form, and we have 2 chlorines. It is also aqueous, so it's in its ion form. But hydrogen is released as a gas. So what you want to go through and do is you want to cancel out the commonalities. So if they show up both on the reactant and the product side, they're what we call a spectator ion. And they're actually not partaking in the reaction itself. And so once you have identified those, you can write your net reaction. And this is the reaction we care about. And this is the reaction we would track and use to determine how are we going to test for the presence of an acid or base or the strength of those acids and bases. So what's left behind? We have hydrogen, we have zinc, and then we still have zinc, so we have an exchange of ions here in H2 gas. And so because there's an exchange of ions from a single ion to a double ion, we can actually look at what's the how vigorous is the reaction going to be, what is its electrical conductivity going to be. There's a lot of things we can predict if we know this information. But also, this example right here is why acids have corrosive properties. Because they're going to react with metals, and they allow metals to turn into an aqueous solution. That means you're literally dissolving the metal away. However, metals have a range of reactivity. If it's an alkali, like your sodium and potassium, it's very explosive. But if it's more like a transition metal, like gold, copper, silver, those are very inert metals. They don't react readily, which is why we use them in piping and in jewelry and all these structures because it's safe to use. So it's interesting to see how we can use these properties. The next reaction we're going to look at is when we do just a straight acid and base, as we know. This is a traditional strong acid base reaction. And these are called a neutralization reaction. Okay. So what this looks like is we're going to truly neutralize all the important ions, and you're going to see why. So if we have HCl, and it's aqueous, and we react it with sodium hydroxide, and that also is aqueous, we're going to produce a salt, sodium chloride, and that's aqueous, and water. Now I'm going to show you why we call this a neutralization reaction and what we consider a traditional reaction. So now we want to go through and make it into our net ionics. So that means we have H plus Cl minus plus Na plus OH minus gives us Na plus Cl minus plus H2O. Identify your spectator ions. So Na plus is on a product, it's also a reactant. Cl minus is a reactant and a product. So we've gone through and we canceled out the common ions. Well, let's look and see what's left behind, right? We have H plus OH minus. That makes water, right? And that water, as we understand, is a pH of 7.0. It's a neutralization. And so that means we've essentially nullified the effects of an acid and base. And so what we can look at is looking at the enthalpy of neutralization. So going back to topic 5 in energetics. So you can look at the change in that enthalpy, or the delta H of the neutralization reaction, and that occurs when an acid and a base react to form 1 mole of water. And so when you have a strong acid and a strong base, okay, and they're going to go through and they're going to make their salt and they're going to make water. Well, what they see, and this is pretty consistent across no matter if it's strong acid, which strong base, they release 57 kilojoules per mole. And so it's an exothermic reaction, as we know from topic 5, but it isn't actually measurable. So we can look, if we're trying to identify how, like, the strength of acids and bases, we can do this. We can collect the data on the enthalpy change to see where it lies. And if it is both strong acid, strong base, that lies at 57. If it's anything less than a strong acid and strong base, you're going to have a lower delta H value. So it's just another way for us to identify the strength. Now, ways we can use neutralization reactions. If you have acidic soil, you can add a weak base, and that's going to neutralize the soil, like lime. If you have like acid indigestion or heartburn, you use an antacid. So you use a weak base to neutralize that strong acid in your stomach, so on and so forth. So this has a lot of medical and environmental situations that we can use. The third reaction is an acid with a carbonate or a hydrogen carbonate. They produce the same thing. So you get salt and water and carbon dioxide. So a sample equation is if we have HCl reacts with calcium carbonate. And what happens is you get a salt, so calcium chloride, water, and carbon dioxide, because it bubbles. So if we go through and we write our net ionic, it's a long one. So we have 2 hydrogen ions plus 2 chlorine ions plus calcium 2 plus and carbonate 2 minus. You get calcium 2 plus 2 chlorine ions plus water plus CO2. Cancel out your spectators. So chlorine, calcium, calcium, chlorine. And you're left with, and it's actually an interesting process, so you're left with essentially HCO3. Well, HCO3 is a weak acid, and that is going to naturally break down into, it's actually H2CO3, and that's going to naturally break down into H2O and CO2. So whenever you have a bicarbonate like that, or carbonic acid, and this is what happens in oceans, because it is a weak acid, it dissociates into these ions, and those ions then further dissociate to make water and CO2, which are completely harmless, right? But this tells you, this is what's called effervescence. So reactions with acids where gas is being released. So this is very common, like an Alka-Seltzer reaction, because you see that bubbling. And so this kind of that's what's happening. So you're working with a carbonate and it's releasing CO2 gas. So how can we go through and distinguish an acid or a base? Well, we use indicators. And they're actually, indicators are either acidic or they're basic, because they need to be able to react with one or the other. Now how they work is they're going to change colors reversibly. So they can go in one direction and then they can reverse back. And it's all going to be based on according to the hydrogen ion concentration in the solution, because that's literally what pH stands for. pH, P to the hydrogen ion concentration. And so understanding what that concentration is will tell us what the pH essentially is as well. So an example is litmus paper. That's the most common form of an indicator. So it's just a strip of paper. If the paper turns pink, an acid is present. If it turns blue, a base is present. However, because it's just turning one color or the other, It does not distinguish strength. Therefore, it does not show the pH value, but just whether an acid or a base is represented. Section 22 in your data booklet will give you a list of common indicators and their pH range. As you know from last year, you know that many of our indicators are from natural substances, like berries and food sources, right? We have what's called a universal indicator, and this is actually a mix of several indicators, which means it changes colors many times, and that allows us to measure the pH. So for every pH number, there is a change in color, and that's essentially what you guys tried to make last year. And when it changes the color, and you know the color is associated with a specific pH value, you can then correlate that to the hydrogen ion concentration, and therefore determine the strength of your acid and or base. Lastly, where we use indicators are in acid-base titrations. And we run an acid-base titration for a neutralization reaction. So what happens is we use the titration to calculate the exact concentration of an acid or base to the best of our ability. You have to be really good at seeing that color change exactly when it's supposed to happen so you don't overestimate how much indicator you had to use. So you have you add a known standard solution to another unknown solution. Oh my goodness. So if you have like a beaker and you've got your burette, right? You are going to know one or the other, right? So you're going to know if this is your base and this is your acid, okay? You're going to know this is, say, 1 molar acid. This is going to be unknown. And so based on how much you use and how much you put into here until your indicator changes, then you can use your mole ratio to determine what the molarity of your base is. It's actually a really interesting process. And when you do this, you can plot, and you can use this using LoggerPro. And so you're going to see what's called the titration curve. And the point of equivalence is the point where you go straight up and down. So this is your point of equivalence. Okay, at that point, you're going to get a pH value. And so that is going to give you, or knowing that information, you can choose the appropriate indicator for that reaction. So if you know the equivalence point is going to be around 4, pick an indicator that changes color around 4. If you know the equivalence point is going to be at 10, pick an indicator that's going to change the colors at 10. And so you have to make that distinction of what type of reaction are you running, where should the equivalence point be, and use it. If you don't know, put a couple indicators in there to cover a range.